Along Interstate 80, west of Elko, in northern Nevada, the landscape presents an unassuming expanse of sagebrush, low brown hills, a roadside truck stop, a railway line, and a shallow riverbed. Directly beneath the ridges north of that highway lies a structural corridor 64 kilometers long and 8 kilometers wide that has produced more gold than the California Gold Rush, the Klondike, and the Black Hills combined. What makes this deposit extraordinary is not merely its immense physical scale, but that it sat entirely unrecognized for more than a century in one of the most intensely prospected regions on Earth, crossed by thousands of emigrants along the Humboldt River during the 1849 Gold Rush, who walked directly over the ore without noticing a single trace. How does the richest gold district on the continent remain completely invisible to generations of experienced miners? And what does its discovery reveal about the fundamental blind spots of early geological survey? In Australia, a comparable pattern of surface invisibility kept the vast copper, uranium, and gold deposit at Olympic Dam concealed beneath 350 meters of barren cover rock in South Australia until modern geophysical modeling forced exploration drillers to probe rock that showed no surface mineralization whatsoever. For most of its modern historical record, Nevada was never expected to be a major gold producer. It was established primarily as a silver state, an economic and political identity defined in 1859 by the discovery of the famous Comstock lode in the hills above Virginia City. Over the subsequent 2 decades, the heavy industrial operations of the Comstock lode generated vast wealth, funded the rapid urban expansion of early San Francisco, and fixed Nevada's economic trajectory in the public mind. The prevailing scientific consensus amongst 19th century geologists, mining engineers, and independent prospectors was remarkably straightforward. Silver belonged to the fault block mountain ranges of Nevada, while gold belonged almost exclusively to the western slopes and river channels of California's Sierra Nevada. Because of this rigid conceptual framework, every canyon, wash, and iron-stained rock outcrop across Nevada was systematically examined by prospectors trained specifically to identify traditional mineral veins. By 1900, the assumption that any major surface deposit would already have been located and staked was entirely reasonable, given the sheer number of men who had traversed the terrain. However, that assumption rested on a technological and observational paradigm nearly 5,000 years old. Traditional prospecting relied entirely on physical visibility, panning alluvial gravels in creek beds, tracing floating quartz boulders upstream to their source, or identifying wire-like threads of free gold bound within fracture zones in white quartz. Prospecting was fundamentally a discipline of direct visual detection, highly effective only when gold announced its presence to the naked eye. The underlying ore bodies of northern Nevada operated under entirely different geological and chemical rules. The gold did not occur in thick quartz veins or concentrated placer gravels, but was locked within flat, unremarkable layers of fine-grained grey limestone. The metal existed as submicroscopic particles, often smaller than 1 micrometer across, hosted within the crystalline lattice of iron sulfide minerals such as pyrite and arsenopyrite. A prospector could hold a chunk of high-grade ore directly in his hand and discard it as ordinary barren stone without ever suspecting its true value. When the Comstock lode began to exhaust its richest ore bodies in the late 1880s, the economic foundation of the entire state collapsed. Mining settlements that had built early electrical infrastructure, brick hotels, and municipal opera houses emptied within a single decade, and the overall population of Nevada declined by more than 1/3. By the middle of the 20th century, Nevada mining was largely regarded as an historical era that had reached its natural conclusion, leaving behind an arid territory whose primary resource wealth had already been extracted and spent. The invisible gold buried beneath the sagebrush remained completely absent from official government survey maps and state economic assessments. The unraveling of that mid-century consensus began not in the field with a pickaxe or a pan, but on paper in an office. In 1960, a United States Geological Survey geologist named Ralph Roberts published a technical bulletin focused on regional structural mapping rather than direct mineral exploration. Roberts had spent years meticulously mapping and documenting the Roberts Mountains Thrust, a massive regional tectonic structure where an enormous slab of deep ocean sedimentary rock was pushed eastward over northern Nevada hundreds of millions of years ago, completely covering the older carbonate strata beneath. In several key locations, millions of years of surface erosion had carved holes through that upper sheet of rock, exposing the underlying limestone in structural features known to geologists as windows. When Roberts mapped these erosional windows across the region, he recognized a clear and unexpected spatial pattern. Known mineral occurrences across northern Nevada aligned consistently along the linear edges of these exposed structural openings. While the broader commercial mining industry initially paid little attention to a theoretical structural paper published in a routine government bulletin, John Livermore, an exploration geologist working for Newmont, recognized its immense practical significance immediately. Livermore had long considered the possibility that Nevada contained major gold deposits that had escaped detection simply because the metal was invisible to conventional visual prospecting techniques. Roberts's structural mapping provided the precise geographic framework needed to test that hypothesis in the field. Partnering with geochemist Alan Coop, who managed the analytical sampling programs, Livermore focused his field investigations on the Lynn Window north of the small railway town of Carlin. Rather than searching for traditional quartz veins or visible mineral fractures in the hills, the team collected systematically spaced rock chips of dull, unmineralized grey limestone. In 1961, laboratory chemical assays confirmed what their model predicted. The limestone contained significant quantities of gold evenly distributed throughout the rock matrix in microscopic particles. The concentration was relatively low on a per-ton basis, but the total volume of mineralized host rock was vast. Individual quartz veins were irrelevant. The entire rock mass itself was the deposit. Newmont quickly constructed and opened the original Carlin mine in 1965, launching a new era of open-cut industrial extraction. Initial reaction across the global mining industry was cautious, as the extraction process required moving and processing millions of tons of host rock rather than following defined high-grade quartz leads. However, lingering skepticism vanished as subsequent exploration identified a second major deposit along the exact same structural alignment, followed quickly by a third. Geologists came to realize that the initial Carlin mine was not an isolated anomaly, but the exposed northern section of an extensive mineralized corridor running southeast beneath the desert floor. To describe this newly recognized ore architecture, geologists introduced the term Carlin-type deposit into global geological literature, establishing an entirely new classification for disseminated, sediment-hosted gold deposits worldwide. The underlying formation of this extensive mineralized corridor required a precise, multi-stage sequence of geological events spanning hundreds of millions of years of continental history. Approximately 500 million years ago, during the early Paleozoic era, the western margin of the North American continent lay far to the east, near present-day Utah. To the west lay a shallow, warm, tropical sea. Over a period of roughly 150 million years, vast amounts of calcium carbonate mud, marine organisms, and fine silt accumulated on this continental shelf, building thick layers of limestone and dolomite thousands of meters thick. Around 350 million years ago, powerful tectonic forces drove the oceanic crust west of the shelf upward and eastward over the continental margin during what geologists call the antler orogeny. This mountain-building event thrust a thick slab of dense, silica-rich deep-water rock across the carbonate sequence, creating an impermeable cap over the porous limestone beds beneath. Tens of millions of years later, during periods of widespread magmatic activity, deep-seated hydrothermal fluids rich in dissolved gold, sulfur, and trace metals began rising through fractures in the Earth's crust. Upon hitting the impermeable upper rock sheet, these hot, pressurized solutions had nowhere to go but sideways, spreading laterally through the permeable limestone. The acidic hydrothermal solutions dissolved the carbonate material and precipitated gold atoms directly onto the outer rims of microscopic pyrite crystals as they grew within the stone, leaving behind an enormous chemical footprint. But how did this ancient subsurface structure translate into one of the largest mining complexes on Earth? The technical recognition and subsequent development of Carlin-type deposits required a fundamental shift in analytical field methods. Throughout the 19th century and early 20th century, field geologists and prospectors had relied on hand lenses, panning assays, and basic chemical spot tests designed specifically to detect native metals or coarse sulfide veins. These simple observational techniques were completely incapable of identifying gold locked at sub-micrometer scales within the crystalline structures of iron sulfide host minerals. The analytical breakthrough came when John Livermore and Alan Coop systematically applied trace element geochemical sampling to fine-grained sedimentary rock units. Instead of testing only quartz veins or visible mineralized outcrops, they collected systematically spaced rock chips across the Lynn Window and analyzed them using advanced laboratory techniques like atomic absorption spectroscopy and quantitative emission spectrography. These modern laboratory methods allow geochemists to detect trace concentrations of gold down to parts per million, alongside characteristic pathfinder elements such as arsenic, antimony, and mercury that routinely accompanied the original hydrothermal mineralization. Once surface geochemistry defined the broad target outline, geological exploration teams verified the deposit geometry at depth using diamond drill core sampling. Meticulous physical analysis of these cylindrical rock cores revealed that the gold was not concentrated in linear quartz veins, but disseminated uniformly through altered limestone beds over hundreds of meters of vertical thickness. Microscopic examination using high-powered scanning electron microscopy later confirmed that the gold particles were deposited as atomic-scale rims on pyrite crystals during the ancient hydrothermal fluid migration events. This analytical shift proved that the resource was defined primarily by chemical distribution rather than visual indicators. What had appeared to generations of 19th-century prospectors as ordinary, barren outcrop was revealed through systematic geochemistry and diamond core drilling to be a continuous, high-volume ore system of global significance. But how did this single analytical breakthrough in 1961 transform the regional geography, regional infrastructure, and modern industrial footprint of northern Nevada over the decades that followed? The spatial scale and remarkable continuity of the Carlin Trend transformed northern Nevada into one of the most concentrated gold-producing districts in the Western Hemisphere. Exploration and development work continued unabated across 4 decades, routinely exceeding optimistic industry projections regarding resource depletion. Major additions along the corridor included the acquisition and deep expansion of the Goldstrike property by Barrick in 1986, followed by major subsurface discoveries at Cortez Hills in 2002 and Goldrush in subsequent years. In 2019, Barrick and Newmont consolidated their long-standing rival Nevada mining operations into a single joint venture entity, combining open pits several hundred meters deep with complex underground shafts extending past 1,600 meters below the surface. The cumulative production figures reflect the staggering structural scale of the entire system. By 2002, the Carlin Trend had yielded more than 50 million ounces of gold across 26 individual mine sites. Nevada Bureau of Mines and Geology records, alongside long-term regional studies conducted by the United States Geological Survey, place the total mineral endowment, combining historical production with proven remaining reserves, at over 107 million ounces. At current market valuations, this total resource evaluation exceeds 380 billion Australian dollars. To contextualize that figure in terms of physical mass, 107 million ounces equates to approximately 3,300 tons of pure gold. That quantity roughly equals the entire national gold reserve held by Germany, which stands as the second largest sovereign gold stockpile on the planet. While Germany accumulated its national reserve over more than a century of international central banking and global commerce, Nevada's total sits within a single structural corridor that a traveler can drive the entire length of in less than an hour. It is critical to clarify that this valuation represents contained metal in ground rather than net profit in a bank account. Realizing that value requires massive, ongoing capital expenditure in heavy diesel fuel, complex environmental permitting, advanced processing infrastructure, and continuous underground development over decades of operation. Yet as a precise measure of what lay unrecognized within a single strip of dull grey limestone, the calculation stands. None of this vast industrial footprint is visible from Interstate 80. From the highway, the landscape remains an ordinary stretch of sagebrush, low brown hills, a railway line, and a truck stop, completely hiding the massive industrial operations working just beyond the ridge. Unlike the Hiley deposit in South Carolina, where gold was documented in historical records for 2 centuries before changing economic priorities caused it to be temporarily set aside, the Carlin Trend was never mislaid by history because official historical records had no knowledge of it. The gap in early exploration was caused not by physical isolation, but by a rigid conceptual limitation. For 5,000 years, visual detection defined gold exploration. A mineral deposit was expected to show visible metallic luster or a clear association with white quartz veins. That rule held true across thousands of verified claims around the world, making it an extraordinarily successful practical heuristic, and precisely for that reason, an absolute cognitive blind spot. Nevada's richest gold deposit remained concealed, not behind impassable mountain ranges, but behind a rigid definition of what gold ore ought to look like. Once that analytical framework shifted, global resource exploration changed permanently. Carlin-type sediment-hosted deposits were subsequently identified and mapped internationally, most notably across large parts of southern China, where comparable sedimentary systems were located only after Nevada established the definitive geological model. An entire class of major ore body existed globally in substantial quantities, remaining functionally invisible until two geologists in 1961 stopped looking for physical gold particles and began systematically evaluating host rock chemistry. That sequence reflects a consistent pattern in major geological discoveries worldwide. Ralph Roberts was mapping regional thrust faults to understand structural geology rather than prosecuting a mine. John Livermore was pursuing a theoretical model regarding invisible mineralization. Alan Coop was running systematic trace element chemical assays on rock samples that previous prospectors had correctly identified as ordinary unmineralized limestone. The 19th century prospectors who traversed this ground were neither careless nor unobservant. They applied the best established methods of their era, but those observational methods were fundamentally incapable of detecting atomic scale dissemination. Geological mapping and deep exploration along the corridor remain highly active today. Questions persist among economic geologists regarding the exact deep fluid pathways that delivered hydrothermal solutions from the lower crust, and deep drilling programs continue to probe thousands of meters beneath existing workings to determine the absolute limits of the deposit. North of Interstate 80, beyond the roadside truck stop, rail line and low ridges, 380 billion Australian dollars of mineral wealth, deposited atom by atom hundreds of millions of years ago, continues to be extracted from rock that presents no surface sign at all. Which place in your own state or territory always struck you as visually ordinary, despite holding a complex hidden history? Or which aspect of this geological survey surprised you most? If you value detailed geographic investigations like this, subscribe to the channel.